And there is another collab exercise. So let's go into the collab exercise. And then I need to connect it again. Okay. So train your first model. And we are going to import our TensorFlow. So import TensorFlow STF and run it anyway. And then we are going to import the NumPy and then import logging. I don't know yet what it means, but it gets some log. And then we set up our training data. So the first two lines, the first one is Celsius Q and the Fahrenheit A. And I think they put Q for the question and the A for answer. And there are lots of numbers. And all of these are written in NP array, so NumPy array. And then this for statement is for I and C. So there are two indexes. And then enumerate Celsius. So enumerate gives you two things. The first one is the order of your sequence. And then the second one gives you the actual contents of your sequence. So it prints out the following things. So the first, negative 40 degrees Celsius is equal to negative 40 degrees Fahrenheit. Oh, I didn't know that. I knew that the 0 Celsius is equivalent to 32 of Fahrenheit, but negative 40 is actually the same number. And 0 degrees Celsius is 32 degrees Fahrenheit. It just shows you the corresponding though. So negative 40 corresponds to negative 40, and negative 10 Celsius is 14 of Fahrenheit, and so on. And then they introduce some machine learning terminology. So the feature is actually the input of our model is called the feature, and the output of our model is called the labels. So in this example, all the numbers in the Celsius is the feature, and all the numbers in the Fahrenheit is a label. And then each pair is called example. So example is a pair of input output used during train. So in our cases, for example, 22 and 37. So 22 and 22 and 72. 22 and 72 is an example. So in this case, we have 1, 2, 3, 4, 5, 6, 7 examples. And this is just a terminology used by the machine learning people. So we call it input, output, and the number of samples. And that's the usual terminology from the statistics point of view, but they use the different terminology to referring to the same things. And actually, there are reasons why they call this kind of thing as a feature, and this is its label, and you will see very soon. And then we are going to create the model. So we are going to create the neural network model. So the first one is to build the first layer, and we don't know what it okay, so we don't know what it means, but it just set the TF TensorFlow, and inside the keras, and there is a layer, and the layer type is dense, and unit is 1, and input shape is 1. So and we call this layer as, it's not 10, it's L0. So they use the name, so L stands for layer. So layer 0 is just the 0th layer. And the input shape 1 refers to there are only one input. Actually, yeah, there are several inputs, but each example has just one point. And remember that the last time when I show you a picture, and that picture is, say, uh, the 10 by 10 pixels, then 10 by 10 is the input shape for that case. But in this case, we have just 1 point from one example, so the input shape is 1. And unit 1 means that the number of nodes inside the layer, but this is just one layer. And then, so I'm gonna execute this one. And then we are going to use the sequential model. So sequential means the one layer, and then another layer, and another layer. That kind of model is called the sequential model. So first, we build our model with the sequential. And inside the sequential model, there is just one layer right now. And then this is the another way to define a model. So instead of defining the layer individually, we actually, this is more not preferable, but in most TensorFlow examples, use this format here. So it says it is going to use the sequential model, and that sequential model, there is the layer, and if you have another layer, and if you have another layer, then the next line is going to be another layer and another layer, and so on. So we define a model, and then they call it the compiled model. And compiled model means since we just have a layer of a model, but we wanted to optimize in some sense of that layers. And in order to optimize something, and you need to define the objective function, and then you need to define how can we optimize, what kind of optimization technique we will use. So you have to specify at least two things. The first one is loss, and for the loss, we are going to use the mean squared error, and you'll see later what mean squared error means. And the optimizer is the so-called Adam optimizer. So this is just the technique of performing the optimization. So this is the compiler means, so you provide some more information to your model. And then we are going to train our model. And how can you train it? And it's very simple. So model.fit is the way we train our model. And in order to train our model, we need to specify which one is the input and which one is the output. So first we give the input, and we give the output, and then the epochs is another terminology we need to understand, but basically it's the number of iterations. So we are going to iterate 500 times, and verbose is that without that verbose is force. Verbose is force. Okay, let's see what it does. To finish the training, and if I turn this one as true. Then it shows lots of the information during the process. So you can see we are going to run 500 times, and then at each epoch, it shows all the information. So how long it uh, takes and what is the loss of each epoch. And after all these things, it is still running and finish training the model. So if you don't want to see all these kind of things, then just uh, use the verbose is false. And then without showing the details inside details, it just running the model fitting and then print out that we are all done. Okay, and then the matplotlib.py is the plotting library, and the X label is epoch number and Y label is loss magnitude, and we are going to plot the loss during the 500 times. So this is the picture. So at the very beginning of the learning, the loss is actually, so you may think, yeah, loss is a bad thing. So we wanted to minimize that loss as much as we can possible. So with small loss means that we can predict our output very accurately. So that's the meaning of the loss in general. So at the beginning of the epoch, the loss is pretty high, but as we go on to training our model, the loss is decreasing significantly. And then once we finish fitting our model, and we can use our model to predict new number. So for example, the 100 Celsius is equivalent to what? We can ask that kind of questions. And it says it's 211. And the correct answer is 212. But this is the formula. So in some sense, this is the formula from the physics or the actual formula. But we did not tell the actual formula to the model. We just provide lots of input and lots of outputs. And then try to we let the computer to learn the relationship between input and output. And then based on that learning, it predicts the output for 100 is equal to 200. And if you round this number, it's 212. So this is the machine learning. And then we can go a little bit more because, okay, I'm going to use the whiteboard. So what we are doing here is actually this. So we put X and then Y. And we did not say anything about the inside of the node. And of course, this whole thing is called a layer. And we just specify one node inside the layer. That was the unit was 1. And actually inside this node, there is a function, looks like this, plus B. And this W is called the weight. And this B is called a bias. And these two are the unknown coefficients. So for example, X was, say, 0, and then we know the output is 32. But initially this machine put arbitrary number for the W and B, and then produce some output with some random numbers, and then it might be, say, 10. And this is the prediction, and this is the actual number. And if you take the difference between these two and square it, that's called the squared sum. So do you remember that our loss function is mean squared error? So this is the error, and we square it. And then since we have many examples, not just one, we have actually 6 examples. So we need to take the average somehow about this number. So that's why we set the our loss function as the mean squared error. And actually there are lots of different loss functions. For example, if you don't like the squared error, you can use just the absolute value between these two numbers. The one is the actual one, the one is the predicted one, and the other one is the actual one. And this also represents some error. And then the algorithm inside the neural network is to try to find the weights and bias so that the actual loss will be minimized. So that's the mechanism between the inside these neural network models. So we can see the weights with this command. And it says that, yeah, it shows you 2 numbers, and each node has lots of different weights and just one bias. But here is the node. In this node, there is only one weight because our input was the one-dimensional. And that number is 1.8, and this one is almost 32. So that 1.8 and 32 corresponds to the number in this formula. So this example, this machine learning model actually trying to minimize their loss, and then they are able, the machine can be identify the very accurate coefficients of this model. And we can do some more things, but I'm gonna skip this part. So that's the explanation for the this part. Okay. So this is our first neural network model, and of course this is a very simple problem, and we actually know the answers because the data, the input, is related to output with this formula. But instead of providing the formula directly, we just provide the input data and output data to our machine learning models, and then let the machine learning model try to learn the actual relationship. So this is the code. And actually, you can think about in 3 steps. The first one is to, it looks like 2 lines, but actually this is just conceptually, this is just a 1. So this is the model building. So we said we are going to use the sequential model, and then inside the sequential model, we have a layer. In this case, we have just 1 layer, but more generally, we may have many layers. And then once you finish defining your model, you need to provide some more information about the loss and the optimizer to your model. So here we use the mean square error for our loss, but as I said, we can use a different loss for our problem. And then optimizer here is given as the atom. And usually, depending on the optimizer, some problems can find the optimal value much more quickly than the other method, but actually the usual way is the add-on, is the most frequently used the optimizers. So you first build the model, and then you provide some more information to your model, and that's the second thing. And the third thing is just to fit your model. So this is the model that fit. And for this fit, you need to give at least 3 informations. What is your input? What is your output? And how many times you want to run this the learning process. That is the essential part of this fitting. And then the reverse, true or false, it's just the optional arguments. And then once your model is fitted, then you can use your model to predict new value. So model that predict and your new value will give you some more information. So let's see. This is actually I just explained to you. You provide the number here, and then with some random coefficients at the beginning, it predicts a value. And then that predict value is compared to the true value, and then calculate the loss. And then this optimization process is actually adjusting your coefficients so that it will provide a much better loss. So that is called the forward pass. And then after the forward pass, you use the backward propagation, so that the backward propagation is just to adjust the weight and the weight and the bias values so that it can predict some more accurate values. So some more terminology here. The feature was we call the feature was the input, and example is the number of samples. So input output pair for training is the example, and then label is your output, and the layer is a collection of nodes, collection with nodes connected together, and then model is the whole structure of your neural network, and then here dense and fully connected. It's just well, I'm going to explain later, what dense layer means. And weights and bias are the coefficients of inside your node. And then loss is the difference between your original, the correct answer and the output, the predicted value. And MSE is the mean squared error, and it is just one way to measure how bad or how good your model is. And gradient descent is a way to find your minimum. So when you are in a high school, you know how to find the minimum value of a function. And in order to find the minimum value of function, we use the derivatives. And that derivative, the generalized version of the name of the derivative is actually gradient. So you may think that gradient at this time is just a derivative. And we are going to the descending way of the derivative. And then optimizer is the specific implementation of the gradient descent algorithm. And there are many of them, but we use the add-on optimizer. And learning rate is suppose you are going to minimize a certain function, and you are here. And first, you need to calculate the derivative of this at this point, and then going in this way. But how far we go in this way, and that's the meaning of the step size. So you can go very little, or you can go very wider. So you can control your step size, and the machine learning terminology, that step size is called the learning rate. And we put this number as, say, 1, and 1 is too big usually. So we use this kind of numbers for our step size. And batch is the set of example used to during the testing of the neural network. So actually there were only 6 examples, but we are going to use those examples again and again. So those 6 number, and actually you can say that is just a one batch, or you may divide it into several batches. So each batch has 3 examples and 3 examples each. And epoch is the full pass over the entire training set. So there were 6 examples, and if you use all of your 6 examples, then that's the one epoch. And we want to use those examples 500 times. So that means you use those 6 numbers 500 times. And fourth pass is the computation in this way, and the backward pass is the backward way. So in the forward pass, you predict your based on your model, you predict some number, and then backward propagation is to calculate the loss and then try to find the coefficients, so that that was the backward propagation. So that's the recap. And I'm pretty sure you can understand all of them once you see the whole pictures. But since this is just the first step, you might be confused, especially when you see lots of equations and lots of coefficients. At first, it might be confusing, but once you figure it out, then it's not that bad. It's just a simple linear equations. So what is the summary? So in this lesson, you learn some of the basic concepts behind machine learning and how dense layers work. And you trained your first machine learning model to convert Celsius to Fahrenheit. You also learned some of the key terms used in machine learning, such as features. Feature was the input, and example is the number of is the sample, is another name, and label is your output. And you also learn the main lines of code that makes up the skeleton of any machine learning algorithms. So remember that you first build your model, and that was the TF-Keras sequential, TF-Keras model sequential, and then you write down the layers inside your model. That was the first step. And the second step is to provide your model some more information, at least 2. What is your loss, and what is your optimization algorithm? So you need to give at least 2, and that was the compilation. And the third one is fitting. So that fitting, for the fitting, you need at least give 3 informations. The first one is the input. The second one is your output. And the third one is the number of iterations you are going to use. So with those 3 is actually all of the machine learning. So in these some explanations. So if you see these layers. The first one is the input. The input is different from the previous examples. In the previous example, it was just one number, the Celsius. But now we have a picture, and picture is represented by 28 by 28 matrix. So the total number of input for one example is 784. So that's the first difference. So the first difference, the first layer is the so-called the flattened layer. So that means you have a structure of matrix, and then they collapsed all the rows into a big array. So that was the flattened layer. And then next is a layer, and this layer is a dense layer, and dense means if you see one node, then if that node take all the input in the previous node, and every node has that node has that property, then it is dense node. It is called a dense node. So in our previous example, there was a Celsius value, and then there was a node. And since it has only one value from above, so it is always a dense layer because it takes every input. But now we have 784 different values, and if one node takes the 784 different inputs, then that's a dense layer. And in this dense layer, it has 128 units, not just one. So it has many layers, the many nodes here. And then one more thing to notice that it has an activation function. An activation function, and then I'm not sure you can see clearly, it's tfnn dot relu. And relu is just a simple short name for the rectified linear units. And it sounds like something very special, but this is nothing but the max function. So this is the Relu function. So Relu it's very similar to our call option pricing formula, but it's not relevant. But it's just a max between two values, and one is the actual linear combination value, the wx plus b, and then the second component is 0, and you take the maximum of these two values. That's the meaning of the activation here is a Relu function. And this Relu function gives you the nonlinearity. So remember that without the Relu function, everything was just a linear. And you know that any linear combination of linear combination is actually a linear combination. So there is no way to the nonlinearity comes in. But by introducing the Relu function, which is a max function, then you can introduce the nonlinearity. And it looks like very simple, but there are 128 different nodes, and they behave differently. So by combining all of them, and each one has the max function, then the output will be very different from the linear function. And then the final difference is that the output is not just 1, it's 10. So in our previous example, the output was just a Fahrenheit, the data. So this was just a one number. But now we wanted to have 10 different numbers, and we want that 10 different number gives us a probability that a certain picture belongs to, say, T-shirts, or belongs to ankle boots, or something like that. And actually, the max functions of all of the 128 value gives just a number. But how can you make a probability? And that's the meaning of the softmax. So the softmax is a function that provides probability for each possible outcomes. So I'm going to explain here what softmax means a little bit more detail, but just wait for a second. And then this kind of problem is called the classification problem. And the conversion from the Celsius to the Fahrenheit can be called a regression problems. So simply speaking, we divide the machine learning into two different categories. One is the supervised learning. The other one is the unsupervised learning. And primarily, we are focusing on the supervised learning. And in that supervised learning, we also can categorize the problem into two different categories. The one is the regression problem, and the other one is the classification problem. So the regression problem, the output is just a real number. So for instance, the Celsius is our input, and then Fahrenheit is our output. And another example for the regression problem is that suppose we have a picture of an apartment, and then the picture of that apartment gives us the value of that apartment. And that's the another example of the regression problem, because it just gives you the real numbers. But in the classification, we want to classify not just the numerical values. We wanted to see whether this is a cat or this is a dog. Or when you see an X-ray of a patient, and we wanted to decide whether he has a cancer or not. And that kind of problem is called the classification problems. And in this example, the classification problem is to classify an image into 10 different categories. So that's why we call this one as the classification problem. And that kind of idea actually already exists in economics already. So when you take the econometrics course, and you will probably hear that the in-sample test and out-of-sample test. And in-sample test, you use all of your data set to calculate the coefficients, and then using some of your data set to predict how good to test how good your model is. And out of a sample test is that you use only part of your data set, and then to test your performance of your model, you use the other sample data set. But here, the machine learning technique is so powerful, and since there are so many parameters to tune, the 70,000 example sounds like a very big number, but actually the machine learning can memorize everything. So that's very important to split the two things. Otherwise, if the things are getting more complicated, we cannot distinguish the machine actually learns something or it just memorizes something. So the training data set is the data set we use for the training, and then test data set is for our test. And later we can also divide the training data set in different ways, but that is the basic of the splitting data set into two different categories.